Hello and welcome to LSTM, Long Short-Term Memory Model, which is a very famous model in recurrent neural networks, um, which actually arrived as a game changer in sequence modeling. This LSTM actually arrived in 1997, way back earlier in this sequence modeling or time series analysis. And it turns out it's still really powerful and very, very useful whenever it comes to the sequence modeling or recurrent neural networks. Before actually diving into what is LSTM, let me just focus on this name of LSTM, which is long short-term memory. If we split this name into certain parts, let me split the name as short-term memory. That's one split, short-term memory, and then the other word is long. Let me have this word, long. So basically, if you now see long, the short-term memory. So in this network, there will be a notion of short-term memory, and the goal of the model is to longer that short-term memory to be useful. So all the network will be doing is there will be a short-term memory, there will be an information that may lost very quickly, that may be gone very quickly, but we want that information to be there for a long period of time, and that's where this name long short-term memory. Maybe we should write the name as longer the short-term memory, if we I don't know, but that's long the short-term memory, or the short-term memory should be longer, something like that. Anyways, there will be a notion of short-term memory, and we want the short-term memory to stay longer, and the short-term memory will reflect some of the information that should be preserved for a large amount of time. And it turns out that this LSTM, although a very classical work, appeared in 1997, it's still very useful, although a lot of variants of it actually appear recently. One kind of similar kind of idea, but a relatively simpler and also very useful idea is GRU, gated recurrent units, that also addresses the same kind of problem and a similar kind of manner also. But it turns out that LSTM, although appeared in late 90s, actually is still really powerful. Because this long short-term memory LSTM is actually appeared in the context of recurrent neural networks. Let me start this tutorial by introducing very briefly what is a recurrent neural network and what's the problem in recurrent neural network that actually brings the need of maintaining the short-term memory for longer period of time. Why the simplest, why the ordinary recurrent neural network cannot hold this, cannot maintain the short-term memory for long period of time. And then we will see how this modification to simple RNN, which is LSTM, how actually it solves the problem of maintaining the information for longer period of time. So let's dive in. A recurrent neural network can be thought of as an ordinary neural network, but there is a layer, or the whole set of layers, that actually give their state back to themselves, and the state information that they give back to. So at one time step, the state of the output state, the state of the network, is actually serves as an input for the next time step. And this kind of input and output relationship, the back loop, can go with respect to the total number of time steps, the inputs or outputs or both can have whatever the maximum is. And it turns out that recurrent neural network can be written as in the form of ordinary neural network if we just redraw this picture, but rather than unroll this loop into a sequence. So for example, at the first time step, you compute there is a state of the neural network, and that state acts as an input for the same kind of layer, same neural network for the next time step, and the state is updated, and that goes on and on and on if the input has t time steps. And it turns out the neural network, the ordinary neural network, if we unroll it in this particular fashion, the depth of the neural network, with sometimes called the deep neural network, the depth of the neural network, although it has one depth in terms of how many layers are there in the stack of net, the other notion which is more crucial is how many unrollings of the neural networks are there in time, because these number of unrollings actually give the depth can be very horrible and very long. So it turns out that recurrent neural networks, they are actually very, very deep. You can design an ordinary neural network by stacking different layers one on top of the other, but it turns out when it comes to recurrent neural networks, the dimension time actually may be thought of as exponentiating that factor of depth. In terms of total number of time steps in inputs and outputs, the total number of layers each neural network here can be thought of as layer processed from left to right. So the total number of layers are way more than any ordinary manageable neural network, and that's precisely actually the cause of the problem, where the information cannot be retained for a long period of time. It turns out that in very deep neural networks, there is a problem called vanishing gradient problem. The vanishing gradient problem, in a very casual form, is the following. You have some criteria, sometimes known as the error function or loss function, or some criteria to guide the neural network. How should it behave and how should it adjust its parameters? And so you present a particular, let's say, example, input instance to the network, and whatever the network state is, and by the way, here I'm not referring to this problem to any recurrent neural network. Here I am explaining the vanishing gradient problem in general term. So you present this input instance to the neural network, and neural network, whatever its state is, produces some output. Based on this output, there also is a required output, and the criteria, there is some criteria sometimes known as the error or loss function. It actually tells whether the produced output is acceptable or not. If it is not acceptable, somehow from this particular criteria, the information that the current state of the whole neural network is adequate, is better or not, it is actually meeting the criteria or not, this information has to be actually propagated back to whole neural network, and somehow the neural network will readjust itself to actually meet the criteria. It turns out that this information that flows back is mostly the derivatives, the gradients, because these are the directions of the gradients in which the error or loss function actually minimizes the most with respect to the training step, sometimes called the learning rate. So these gradients, they flow back, and based on these gradients, the parameters or the states or the parameters of this neural network, they actually is changed or updated, and then the process repeats until a particular criteria is met. It turns out that in very deep neural networks, as this gradient flows back, in fact the gradient flows back in a chained fashion, which means the previous gradient somehow is multiplied with the other gradient, and the gradients, they are multiplied together to reach the very earlier layers of the neural network. These kind of a lot of products, specifically reaching to the earlier layers, they actually cause two kind of problems. A lot of products, they actually bring the gradient to very small number. So think about, just for intuition, think about a lot of numbers that are all very small numbers. If you multiply all of these numbers together, the result is really small. or the reverse way, if you have a lot of numbers in the product and all of the numbers or most of the numbers are really big, then the product is expected to really big. What happens is either when the gradient becomes very small or it becomes very, very large. In the case of small gradient, the training actually doesn't happen. The earlier layers, they actually do not affect the error function, which means whatever the information is here in these layers, that is not propagated better to the loss function. And in terms of exploding gradient, when the gradient is really large, actually the training process or the process of finding out the minimum become minimum error or loss become really unstable. It, however, turns out that there are some practical solutions for exploding gradient. One is known as gradient clipping. And the simple solution, gradient clipping, is that if the value of the gradient is larger than a particular threshold, then you just clip the gradient then just restrict the gradient manually to a particular value. But however, it turns out that the vanishing gradient problem is a bit more complicated and a bit more serious. And it appears when the depth of the network, when the number of layers of the networks are really large. So as a function of number of layers, the problem of vanishing gradient can be thought of as a relationship, maybe linear or superlinear or something like that. So if we can define the problem in a quantitative way. So in recurrent neural networks, depending upon the time in the input, in the sequence, the network can be unrolled for several time steps, thereby making a huge and very deep neural network, and the vanishing gradient problem becomes a natural bottleneck in that. Effectively, what happens, what vanishing gradient problem brings in deep neural networks, and particularly in recurrent neural networks, the information at earlier time steps, it does not impact the loss function or the long-term dependencies. They actually are lost. Although you can have a short-term dependencies, so the criteria depends on the short-term memory or the information, but the long-term dependencies are lost. And in several cases, the long-term dependencies are really, really required, which actually is the biggest problem of this vanishing gradient problem. So don't worry, LSTM, actually the long short-term memory, is actually the solution of this kind of problem. Here, I'll explain this LSTM model in a completely casual and understandable way, and the abstractness of the explanation will be a little bit high. I'll not be going into the very details or equation level details in this slide, although we will write certain equations and how these kind of things are implemented after we build an intuition what happens. First of all, what do we mean by short-term memory? So what is short-term memory? So how it is modeled, short-term memory. It turns out that the internal state of neural network can be thought of as short-term memory. So for example, the activations, let me write the activations of neural network at time t minus 1, they can be thought of as short-term memory for time t. That's a short-term memory. Or maybe we can have, there are multiple ways of modeling the short-term memory. One very powerful way of modeling the short-term memory is to model the memory or the information that we really want to retain as the state of the neural network. And one powerful way is to model the state as to just model the memory as the activations at different time steps. So we want to maintain the activations or the memory if required for a longer period of time. So what that really means, maybe the activations or the state for very earlier timestamps may be required after a very long period of time, and we may want to retain that as it is. thereby not disturbing the rest of the flow of the network. So first of all, we model the memory as the state of the network. That's our memory or the activations. How to longer those? There are three ways to there are three kind of ways LSTM manages to keep or throw the information away. One is there are three kind of gates. The LSTM, long short-term memory, it actually uses three kind of gates. Here you can see this particular box. Think this particular box just as a gate, and think a gate as a decider whether to do this stuff or not. That's kind of a binary decision maker. Do this or don't do this kind of. So there are three kind of gates. Let me write the first gate as the keep gate, and the second gate might be the write gate, and the third gate might be the read gate. Although in literature, in this recurrent neural network literature, the keep gate is really the gate sometimes known as the forget gate. The renamed version is forget. The write gate is really the update gate, and this read gate is sometimes known as the output gate. But I will follow this keep, write, read because it brings beautiful intuition of understanding LSTMs. And by the way, I have borrowed these words keep, write, and read for LSTM from Jeffrey Hinton. He's a big name in deep learning. So in his video lectures and slides, he used the word keep, write, read instead of forget, update, and output. So I'm using keep, write, read just for illustration. So think about a keep gate that either has value, keep gate either has value, or a keep variable or a keep flag that has value between 0 and 1. And consider information in a particular memory cell. That's, let's say, a memory cell. We have defined a memory cell in which the memory or short-term memory will reside. And the keep gate guides whether we want to keep the value that is there in the memory cell or we should not keep it. So for example, if the keep gate is on, then whatever the memory cell, whatever the information there is, the memory cell will stay as it is. And who will update the keep, who will decide the value of the keep gate? That the rest of the network, the rest of the network will actually decide what should be the value of the keep gate. Actually, this is the part of the training process to find out the values of the keep gate for different training data. So the rest of the network will decide the value of the keep gate, and if the keep gate value is 1 or on, that means whatever there is in the memory, that will stay in the memory. And if the keep gate value is 0, that means whatever that is in the memory, I should just throw it away or forget it. The next gate is write gate. So again, that's the memory cell. So think about write decider or write gate. If write gate is on, then this memory cell is available for writing, overwriting, or update. Then we will write another state or another information that we may want to retain for longer, and we will update the memory cell, we will update the information. If the write gate, however, is off, it has value 0, then we will not allow the memory cell to change its contents. So this write gate or update gate actually works as whether we are going to update the contents in the memory cell or not. Again, who will decide what should be the value of the write gate? Again, the rest of the neural network as a part of its training. Because these are the keep gate and the write gate, they have their own trainable parameters that will be trained and adjusted through the backpropagation, just as the other parameters of the network. The one last gate is the read gate, or sometimes known as the output gate. Again, it has two states. It is either 0 or 1. If read gate is 0, that means we no longer want the information to be used for the rest of the networks, for the rest of the neural network. And if the read gate value is 1, that means the information in the memory cell is required now, and just read that and utilize it and influence the rest of the recurrent neural network. And the whole recurrent neural network, this is just one cell, which is LSTM. This is just one cell. The whole rest of the recurrent neural network is actually managing these gates. So you can now think the information flows, the information is exactly like the same, but which information should be flow in what kind of direction, and what information should be kept as important or as unimportant, or influential in long term or not influential in long term, is decided or triggered by these kind of gates or controllers. So think about a recurrent neural network layer having these kind of controllers, and these controllers are trainable. And having these controllers, it is possible to actually keep the information for a long period of time, and the information will be kept in a separate memory cell, and this memory cell contains the short-term memory. And if the keep gate is on for a longer period of time, the short-term memory for stay longer in the neural network, thereby avoiding the impacts or effects of vanishing gradient problem. Yeah, so that's how this LSTM works. Let me describe some of these variables. Here, this C or M t minus 1, that is something in the memory that may be required next time. This is basically the activations for the previous time step, and this is the input for the current time. And these are the activations for this time, and this is the information or the contents of the memory cell for the next time step. Similarly, this path actually receives the activations and may lead towards the output. In the next slide, I'm going to actually describe some of the mathematical details that are there in these kind of diagrams. So this is basically a logistic gate, logistic function which has basically minimum value 0 and maximum value 1, depending upon the very negative contents and the very high magnitude positive contents respectively. Think about this as a forget gate. So forget gate, gate forget, or you can call this as a reverse keep gate, whatever. And this is, let's say, the information in the memory that is stored in the memory, and these are the activations or state of the network. And this is the input at the current time. Now, for example, this gate will decide whether this operation is going to happen or not. So, for example, let me generate this value C for the next time step in the following way: the candidate value. So the candidate value for the next time step in the memory cell can be turned as the tan H and some parameters times the previous activations and the previous input, the current input, along with some biases. I'm assuming that the biases are handled inside the weights. So that's the candidate for the memory cell. Consider a memory cell there. Consider a memory cell. Already the memory cell contains the information C of t minus 1, and that's exactly the information, that's exactly the short-term memory. And this is the information that is candidate to be updated to update this memory cell. Now, whether this information is allowed to update this memory cell or not, it is decided by an update gate. So let me define the value of the update gate, which is here, the update gate. That's the update gate or input gate, sometimes known as input gate or update gate. That's the gate. It is basically defined as the sigmoid of its own parameters that are learnable parameters, the previous activations, and the current input. Again, I'm assuming the biases are handled inside the weights. Ideally, there should be a function that exactly gives 0 or 1, not the value, because the gate value should be binary. But it turns out implementing a straight 0 and 1 function has some problems in backpropagation, particularly when we compute derivatives. And it turns out that logistic sigmoid is a reasonable differentiable approximation of that, considering a value inside to be very large correspond to a gate value to be closer to 1, and the inside value in the logistic to be really negative or large negative value actually pushes the gate value to be closer to 0, which serves the purpose. So ideally, these gates should not be logistic functions because logistic function does not have a range just 0 or 1, although it has a continuous range, but logistic function is a good approximation and it is required for a smooth backpropagation. So this update gate or the write gate will decide whether this information is going to be written in that or not. Further, we have a keep gate, or the reverse of keep is forget gate, that has again its own parameters. And a t minus 1, it actually takes the activations of previous time, and the current inputs, again the biases are assumed to be handled in the weights, and that's the forget gate. Now the value that should be there in this memory cell, the exact value in the memory cell, is whether we are going to update the previous the update using this value, which is the c tilde t, or we are actually going to keep the previous value. So keep the previous value, which is ct minus 1. So just think of, intuitively, just think this combination as if the update value is 1 and the forget or the keep gate is again the forget value is 0, then what will happen is we will update the memory with the new contents, and we will keep that memory as long as the keep gate is on. And on the other hand, if the update gate is 0 and this gate is forget gate is 1, then we will keep the original value as it is and we will not update it. So either this memory will pass through the network as it is, or it will be updated to a more recent memory that might be required. And last, how actually this read gate or output gate works. There is an output gate, let me call it as GO, which has its own parameters, and it depends upon, again, the activations, previous activations, and the current input. The biases are assumed to be handled there, and these activations AT, they are basically computed just if we want to read those or not. So G naught times tan H CT, whatever the CT is, because we might have updated the CT with the new value, or we might have kept it as it is. And here we may want to use it or read it, or we may not want to use it. And all these parameters, if you think here, the parameters like these parameters, and these parameters, these are gate parameters. Other than these kind of parameters, these are gate parameters. And the rest of the network through the training data actually get the best values of these parameters. And it turns out that this particular cell, LSTM cell, works very, very well for maintaining the information for a very long period of time, very, very long period of time, thereby avoiding the problems that are caused by the vanishing gradient. Let me just close this video by telling you how can you implement, or what is the command inside the TensorFlow for LSTM. So import TensorFlow. If you just work in TensorFlow as TF, so in the sequential model or whatever model you are working with, you can add a TensorFlow layer, LSTM layer as TF. So for example, layer as tf.keras .layers.l LSTM, and here you can add LSTM, for example, for 200 units, and that's a layer. Obviously, this layer should not be used alone. Normally there are some layers on top of it. Normally there are some layers that are output layers, and there are a lot of recurrent neural network models in which this particular layer could be used. So that's about LSTM. I hope you have enjoyed our video. If you did, then please press the like button, subscribe our channel, and share this video with your fellows. Hope to see you next time.